In Clarke's vision, the computers of yesterday paved the way for the omnipresent intelligence of today. Welcome, how may I assist you with your data visualization?
Welcome to this explainer. Today, we are unpacking something I find absolutely fascinating: the magic of predictive intelligence. You know, the tech we interact with every single day has recently crossed this massive, almost unbelievable threshold. And we're going to dive right in and explore exactly what is powering this crazy modern reality of ours. To really set the stage for this, we have to start with this incredibly audacious statement made by Arthur C. Clarke way back in 1962. He said, "Any sufficiently advanced technology is indistinguishable from magic." Now, when Clarke proposed this, his famous third law of prediction, it was pretty much dismissed as just a sci-fi writer's rambling. But to really grasp why this matters so much to us right now, we have to kind of put ourselves in the world he lived in when he actually made that claim. Think about it. In 1962, computing meant these massive, literally room-sized machines. I mean, they generated enough heat to bake a cake, but they could barely handle basic arithmetic. Now contrast that with today. We literally carry these miraculous pocket-sized devices everywhere we go. We speak into thin air to invisible assistants, right? And we rely on systems that can diagnose complex diseases from just a single scan. Clarke's magic isn't just arriving someday. It is already right here in our pockets. So what does this all mean for us? Well, this isn't just about, faster silicon or having brighter screens. We are experiencing a truly fundamental shift in how human beings interact with knowledge, with power, and honestly with reality itself. It's kind of like the discovery of fire or the printing press. It completely rewires how we live and how we govern ourselves. But unlike a roaring fire, this modern transformation is incredibly subtle. And the driving force behind this subtle shift is predictive intelligence. Basically, this is technology that learns, adapts, and actually anticipates our needs entirely without a manual, without being explicitly told, and very often without our full awareness. It doesn't just execute a command you type in anymore. It anticipates your intent before your finger even hits a keystroke. And this intelligence is quietly embedded absolutely everywhere. It's in the navigation systems that magically route you around an accident that literally just happened seconds ago. It's meticulously curating your social media feeds to keep you constantly engaged. And on a much, much bigger scale, it's quietly powering global financial markets, moving trillions, yes, trillions with a T, of dollars based on these incredibly complex predictive models. Seriously, if Clarke stepped out of a time machine today, he'd see his magic silently running the entire global economy and your morning commute, all at the exact same time. Now, it's one thing to just accept that your phone can anticipate your needs, but we really have to ask, how does a machine, just a collection of metal and silicon, learn to understand the incredibly messy, complex nuances of human language? How can a purely mathematical algorithm look at an image and identify a potential health risk before a patient feels even the very first symptom? To truly understand how this magic is real, we've got to peek behind the curtain and ask the most intriguing question of this whole explainer: how does this magic actually work? Well, the answer lies in something called an artificial neural network. And these aren't just, basic strings of random code. They are highly complex networks of mathematical equations that were directly inspired by the biological structure of our own human brains. By layering these networks, machines can process information in ways that closely mimic, and honestly, in some specialized cases, completely surpass human cognition. This right here is the engine making all of this predictive intelligence possible. Now, given how totally dominant these neural networks are today, you'd probably assume this was just some recent stroke of Silicon Valley genius, right? But here is where our story takes a really brilliant and completely unexpected twist, because the path to this reality was absolutely not linear. The journey to this technological magic was actually filled with dramatic highs and some pretty devastating lows. Believe it or not, the original concept for the neural network wasn't born in the 2000s. It was actually theorized all the way back in the 1950s. But it definitely didn't take off immediately. In fact, it was followed by literal decades of profound failure. We're talking years marked by intense ridicule from the scientific community, drastically slashed funding, and completely abandoned research. People widely considered it a total dead end. Yet, against all odds, it somehow survived that long, harsh winter to emerge as a defining technology of the 21st century. So, this incredible journey from total ridicule to absolute triumph really leaves us with one massive, lingering question. What hidden chain of quiet, completely overlooked moments actually saved this forgotten idea from the 1950s and brought us to the threshold of Clarke's prophecy? The answer doesn't lie in one single loud eureka moment. It's all about the stubborn persistence of researchers who just refuse to give up on a dream. It really makes you wonder, doesn't it? As we look toward our future, what other totally dismissed ideas are quietly waiting in the wings right now, just getting ready to become the magic of tomorrow? Thanks so much for joining me on this explainer. And hey, keep your eyes open.
Imagine a machine that can understand human language. The possibilities are truly limitless if we can achieve true symbolic reasoning. We did it! It actually worked!
The confidence score is off the charts. This changes everything.
Welcome to This Explainer. We've got a truly fascinating story for you today. It's all about how decades of unyielding and, honestly, often completely ignored human curiosity eventually unlocks something that feels, well, practically magical. We're talking about machine creativity that was literally fueled by that very human curiosity. We're going to peel back the layers on the hidden history of artificial intelligence to see exactly how we got from these brittle, failing early machines to the systems today that can paint, write, and compose. Okay, let's dive into this. On the left here, we have the early days of AI. These systems were rigid, they were brittle, and they were easily defeated by the absolute simplest tasks. I mean, literally things a toddler could do without even thinking about it. But on the right, we see the startling reality of modern AI. Today, these same kinds of systems are seamlessly translating languages, composing original music, and even writing pretty convincing poetry. It's a massive leap from rigid logic to fluid creativity. So how on earth did that happen?
Let's start with Section 1, the 1956 Dartmouth Illusion.
To really understand this, we have to start our idea's hero's journey at the very beginning. The story kicks off in 1956. A small group of scientists gathered at Dartmouth College for a summer workshop. This was a monumental event because they actually coined the term artificial intelligence. They were incredibly optimistic, convinced that within just a decade, machines would be entirely capable of learning, reasoning, and solving problems exactly like humans do. But yeah, they were spectacularly wrong. They tried to build systems based on strict top-down rules, and reality very quickly defeated those rigid constraints. Let's just quickly map out this 60-year journey so we know where we're going. We start with that 1956 Dartmouth birth. Then, things take a dark turn as we plunge into the 1970s, an era infamously known as the AI winter. From there, we'll jump to a deeply controversial 1986 breakthrough called backpropagation. And finally, we reach 2012, the ImageNet thaw, where the whole game changed forever. Which brings us to Section 2, surviving the AI winter. After that initial 1950s hype faded, the field faced a massive, painful reality check. By the 1970s, the optimism of Dartmouth had just completely evaporated. Funding for research dried up entirely. We entered this deep period of disillusionment that dragged on for nearly 2 long decades. Researchers were essentially forced to abandon their dreams because the pressure against the field was immense. It got so bad that the very phrase artificial intelligence became almost taboo in academia. I mean, nobody wanted their career tied to a failing concept. So the crucial point is, what was happening while everyone else was looking away? In the shadows, a few incredibly persistent thinkers absolutely refused to give up. Their curiosity drove them to keep the dream alive, but they changed their approach. Instead of building systems that followed those brittle, strict rules from the 50s, they began painstakingly building systems that learned from data. It was slow going, and honestly, for a long time, the wider scientific community just completely ignored them.
That takes us to Section 3, the backpropagation breakthrough. That quiet, ignored curiosity was actually building towards something massive. In 1986, a mathematical breakthrough occurred that pretty much nobody saw coming. 3 researchers, David Rumelhart, Geoffrey Hinton, and Ronald Williams, published a paper on a technique called backpropagation. Simply put, this is a method for training neural networks to adjust their internal weights and improve their accuracy over time. Rather than being programmed with rules, the machine could finally learn from its own errors. It was a total paradigm shift. Now you might think they were celebrated immediately for this, right? Not at all. This mathematical breakthrough was deeply controversial. Established scientists completely dismissed as a dead end, saying neural networks were just too slow. And here's the crazy part. The critics weren't entirely wrong. The computers of the 1980s were simply too weak to run these algorithms effectively. This was a moment where human curiosity and theoretical math literally outpaced the hardware capabilities of the era.
And this brilliantly illustrates exactly what happened next. The 1986 theory, as one writer put it, waited like a seed in frozen ground for the right conditions to sprout. The theory was perfectly sound. The curiosity had done its job, but the math just had to lie dormant, buried under the frost of the AI winter, waiting for our computer technology to finally catch up.
The thaw finally arrived in 2012. A team led by Geoffrey Hinton, one of the original researchers from that 1986 paper, used a neural network to compete in the ImageNet competition, which is a major contest for visual recognition. They didn't just win, they won by a staggering margin. Their system was nearly twice as accurate as the previous year's winner. This massive, sudden leap in performance made the entire tech world stand up and take notice. The frozen ground had finally thawed. The AI winter was officially over. Moving right along to Section 4, the superpower of scale. With the winter behind us, the field experienced an explosion of progress that shocked even the original researchers themselves. Let's move to and see how this builds into the modern AI we interact with today. Researchers made one of the most surprising discoveries in the history of the field. Bigger was simply better. The more data you threw at these networks, combined with vastly more computing power, the more intelligent they became. This massive scaling up allowed these systems to finally start grasping intricate context and highly complex relationships within the information they were fed. This realization that scale was everything led directly to a major architectural breakthrough: transformer models. These are systems that can process entire sequences of text or data all at once. Instead of looking at things sequentially, one little piece at a time, they learn the context and the relationships between absolutely every element in a sequence simultaneously. Giving a machine this capability was essentially giving it a superpower. It gave AI the ability to see both the forest and the trees simultaneously. By perfectly grasping wide, sweeping context without ever losing sight of the tiny details, the stage was finally firmly set for genuine machine creativity.
And that brings us to our final part, Section 5, Mathematics, Curiosity, and Creativity.
This is where those decades of isolated math transform into the astonishing creative outputs we see today. Now, what's really interesting about this slide is that it totally dispels the illusion of an overnight success. The lesser-known truth about today's AI is that it is built squarely on decades of ignored research and failed experiments. Those isolated thinkers in the 1970s and 80s, driven completely by their own curiosity, laid the groundwork. And the result of their painstaking, ignored work? We now have machines that effortlessly translate complex languages, compose entirely original music, and write highly emotive poetry. And yet, as immensely powerful as these transformer systems have become, they leave us with a profound mystery to ponder. How could a machine that operates on pure, cold mathematics produce outputs that feel so incredibly human, so brilliantly creative, and sometimes so deeply unsettling? It's a question that challenges our very understanding of art, curiosity, and intelligence. And for sure, it's the question that will drive the next critical chapter in this unfolding story. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll see you next time.
we are seeing the earliest cellular changes. This changes everything, Doctor. If we stabilize the structure here, the AI predicts a 40% efficiency gain. Apply the new parameters.
Hey everyone, and welcome to this explainer. Today we're popping the hood on the systems that basically run our modern world. We're talking about algorithms so intensely complex that they are genuinely starting to resemble actual magic. But more importantly, we're going to unpack the ethics behind black boxes. What actually happens when we can no longer explain how all that magic works? Okay, let's dive into this with a quote you've probably heard before. The legendary science fiction writer Arthur C. Clarke once said, "Any sufficiently advanced technology is indistinguishable from magic." For decades, that was just a fun thought experiment about some distant, unimaginable future. But looking at the source material today, that vision, it's really no longer confined to science fiction. It's our present reality. We are completely surrounded by systems so advanced, they literally feel like magic to the everyday user.
Section 1. Magic in daily life. It's already here.
Let's move to this and see how it builds, because this magic isn't something waiting for us in the next century. It's actively embedded in the fabric of our daily routines right now. It starts small, right? Predictive text anticipates your next word, maybe revealing that you type the word pizza way more often than you'd care to admit, or streaming algorithms perfectly curating your Friday night movie based on your past behavior. But the stakes escalate rapidly. When we look at high-tech medical imaging, we go from a machine finishing a mundane sentence to a machine fundamentally altering the course of a human life. We shift from pure convenience to immense consequence.
Section 2. The medical miracle, a matter of life and death. And this brilliantly illustrates what happens when we apply this tech to the healthcare sector, where the awe-inspiring power of these algorithms truly comes into focus. Researchers have developed neural networks that can detect cancerous cells in medical images with a level of accuracy that actually exceeds highly experienced human radiologists. Think about the gravity of that for a second. We are talking about medical professionals with decades of intense, rigorous training, people who have dedicated their entire lives to visual diagnostics. And these algorithms are just consistently outperforming them in spotting anomalies. The machine is seeing what human eyes, no matter how highly trained, might totally miss. To really ground this in a real-world example from our sources, consider a recent study where an algorithm identified a rare form of breast cancer. And it didn't just identify it, it detected it years before any actual symptoms appeared in the patient. What does years before really mean in this context? Well, it means the difference between a proactive, manageable treatment plan and a desperate, late-stage fight for survival. Early detection on this kind of scale means potentially saving countless lives that would otherwise have been lost to a delayed diagnosis. It is, for sure, a genuine modern-day miracle happening right now.
Section 3. The black box dilemma. Power versus opacity.
But with this incredible power comes a very sudden and, frankly, troubling challenge. On one side, we have systems mastering these super complex environments and literally saving lives. But on the other side, troubling opacity. When an algorithm flags a medical anomaly, researchers and doctors often cannot retrace its steps to see exactly how it got there. We have the what, the brilliant life-saving diagnosis, but we are entirely missing the why and the how. We are basically handing the steering wheel of human health over to a driver who won't or mathematically can't explain their route. So the crucial point is really this definition of a black box. Data goes in, brilliance comes out, and the space in between is utterly dark. But applying this to complex, high-stakes environments elevates the ethical stakes immensely. It's no longer just a weird technical quirk, it's a massive barrier to accountability. Relying on an opaque system to make critical decisions forces us to ask who is actually responsible when the magic fails. If a doctor can't understand the underlying logic of the AI's decision, how can they confidently sign off on a life-altering medical procedure? Section 4. Bias, privacy, and power, the ethical pillars. To truly grasp the impact here, we have to look at three primary societal domains where this opacity causes some major friction. First is bias. Because opaque algorithms are trained on vast troves of historical data, they risk quietly amplifying existing inequalities. Without a clear view into their logic, these biases can be baked right in without anyone detecting them. Second is privacy. Achieving that magical accuracy requires an unprecedented harvesting of our personal, sensitive data, raising some really deep questions about surveillance and ownership. And third is existential power. What happens to human agency and our societal structure when machines consistently outperform us in increasingly complex, traditionally human domains? To highlight those existential implications, let's look at the ancient game of Go. This is a game of deep intuition and strategy, with more possible board positions than there are atoms in the observable universe. Let that sink in. It was widely considered the absolute ultimate test of human intuition, and experts thought machines were at least a decade away from mastering it. But an algorithm conquered it early, executing moves so wildly unconventional that human masters initially thought they were just glitches in the system. If an opaque machine can master that level of unimaginable, nearly infinite complexity, we have to ask with absolute gravity, what other boundaries are going to fall next?
Section 5. We are the magicians, from fear to empowerment. Now, what's really interesting about this slide is that it's so easy to look at black boxes, invasive data privacy concerns, and superhuman algorithms and just feel a deep sense of dread. But our true strength isn't our raw computational power. We will always, without question, lose that race to the machine. Instead, our greatest assets are our deep human curiosity, our uniquely human empathy, and our ability to dream. These are the ethical and philosophical frameworks that a machine simply cannot compute. These uniquely human traits are what will ultimately guide the responsible development of this technology, far surpassing any raw algorithmic output. We are not passive observers in this technological transformation. We're the architects. Arthur C. Clarke's vision of advanced technology being indistinguishable from magic, that wasn't meant as a dark warning. It was an invitation. It was an invitation for us to rethink what's possible, keeping in mind that this magic is entirely of our own making. It's a reflection of our profound, enduring desire to improve the world, cure disease, and expand the boundaries of human knowledge. We are standing on the precipice of an entirely new era. The machines we build may indeed become indistinguishable from magic, but we will always be the magicians. The question is no longer whether Clarke's prediction will come true. It already has. The question I want to leave you with today is this: what will we choose to do with this magic? Thank you so much for joining me for this explainer, and I hope this gives you a powerful new lens to view the technology shaping our world.